Hello, everybody from FlowCon. Fred and I are excited to be here, with our SysFlow trilogy talk. This is the third year in a row we've had the privilege of being at FlowCon, and so this will be the third talk in our SysFlow series, I guess you'd call it. We're hoping that it'll be an epic trilogy, kind of like the 1980s Star Wars films. But as Shane was mentioning, Fred and I are both from IBM Research. And today we're going to talk about how we can use SysFlow to create sort of a self-modulating endpoint for observability. So in other words, how can we use SysFlow to reduce the number of events and the rate of events that we have to, when we're forwarding on to things like SIMs and the other thing. So, but before we jump into that, we wanted to sort of recap the last 2 years of talks very quickly for those who haven't attended the past couple of FlowCons. How dare you? Or those who maybe slept through the talk. We'll first go through 2020, where we introduced SysFlow, which is basically an open source data format. FlowCon has a sort of a rich history with NetFlow. And so the easiest way to describe SysFlow is that it's NetFlow for system events. So like how NetFlow uses is basically a summarization of network packet captures into connections and summarized events. SysFlow takes rich sort of system call, raw system traces, and summarizes them into a higher level sort of behavioral format. The format is basically process-centric. So basically what it does is it describes or records how a process interacts with its environment. How does it interact with the file system? How does it interact with the network? How does it interact with other processes? And essentially creates a format that is really good for data science activities, for doing analytics, for visualization, and other things like that. The format is also container aware. And the next version of the format will also be Kubernetes aware. So we're going to create sort of objects around, K8s, pods, and things like that to enrich that information. So this just sort of describes a little bit more in detail what SysFlow looks like. So SysFlow is really an object relational format, whereby we have a set of entities, which are things like processes, containers, and files. And basically, we have a set of events and flows. And events and flows are essentially actions that either occur on the entity or by the entity. Events are point in time actions that occur, over the time period or operation of the process, whereas flows are sort of a summarization of multiple events. So, for example, a network flow would be the combination of individual reads or sends and receives on a connection to a particular endpoint. So in this particular example, the green elements are the entities. So in this particular case, we have a process 1822, which is going to clone itself, which would be a process event. The events and the flows in this case are in purple. It clones process 1823, which then execs itself, maybe loading up a new exe image. And then it starts to communicate with different endpoints. So it's communicating on the network and doing lots of connecting sends and receives to a particular endpoint. So we can summarize that information into a network flow that would be similar to a net flow, but at a different level. We also do that with file flows, which would be a consolidation of all of the events that would go to a particular file, either reading that file or writing that file. So in that sense, we lift these raw system events into sort of a set of behaviors that we can then link together, as you can see sort of from this thing, into a graph-like structure, which we'll get into a little bit more detail later on. But the idea here is that the language is designed for this connectivity to give that context that's so important when doing analytics, and also to reduce the amount of data that we have to store, and then to do making analytics easy by loading this format into really any of your favorite analytic toolkits or languages. Last year, we talked about the SysFlow processor, which enables edge analytics. And so if we look at the architecture here, this is the overall architecture of what SysFlow looks like more or less today, whereby we have a collector, which has an eBPF probe or kernel module, which connects into the kernel and passively collects raw system events. So things like reads and writes and execs and all that stuff, and then passes it up into the user space, where the collector then summarizes that information into SysFlow. We then added last year a processor. The processor is basically a host level application written in Go. And that processor essentially allows you to write various analytic plugins and then chain them together to do some overall level of analytics. And you can essentially connect SysFlow in there. You can write other source plugins to bring in different other sorts of data sources. And then, like I say, build your own analytics and your own exporters to export to all the various different types of SIMs or to Elastic and things like that. Within the processor, we also released some core plugins, for example, the policy engine, which actually supports the Falco policy language. So for those who are familiar with Falco and Falco alerts for runtime security, those are available there. And we're also have a graph engine, which Fred is going to talk about a little bit about later on. And we have actually, since last time, replaced the lower end of this graph with Falco Lib. So we're becoming more contributors with Falco and sort of strengthening that partnership there and being more active inside of the CNCF community. We also introduced graphlets, which is essentially this behavioral coalescing. So we can take that SysFlow, create these graphs, which can simplify sort of the behaviors and show the context of attacks as they are occurring. And Fred's going to get into a little bit more detail of this, but we also have in our last talks on YouTube where you can see that some more in terms of how these graphs coalesce behavior and can store state in very much compressed in a compressed form. We also offered MITRE ATT&CK TCP tagging, which allows us, to support TTP alerting and labeling of specific SysFlow events. So now we'll get down to this year's talk, which we want to discuss how to combine these technologies to help reduce event fatigue. So SysFlow, the processor, as well as these graphs and adding them in to essentially rate limit system events as we're sending them to SIMs. And so why is this the logical next step? It's a logical next step because, for example, SIMs tend to charge by ingestion rates. And so by being able to eliminate, reduce the amount of traffic that we're sending in, we can save money and value there. System events can generate a lot of traffic, which can create a lot of excessive noise and redundant alerts, which can either hurt the analyst and cause them to shut something down, or they have to continuously manually tune these set of rules to get the events down. We propose sort of an automated reduction and to a system that will automatically reduce that, so we don't have to do that manual process. And by reducing these events, we can reduce our resource usage both on the endpoint and at our where we're doing analytics and things like that. So here is basically an overview of our system telemetry stream modulation or rate limiting system. And basically the big takeaway from this particular visualization is that if we start from the left, we're getting very raw and coarse system telemetry. And at each stage as we move along, we're able to summarize and contextualize that information to be able to help us build a rate limiting, contextual rate limiting system. So we take the system calls, they come in at high frequency, we summarize them down using our SysFlow data format, then we coalesce them using those particular graphlets, and at each level or stage in the pipeline, we can reduce the amount of data that we have to deal with, which allows us to increase the amount of state that we can store. And so at the graphlet level, we can start adding in other data structures, which allow us to do better rate limiting, smarter rate limiting to be able to push those alerts out. So now I'm going to pass it over to Fred, and he's going to talk a little bit more in detail about the rate limiting aspect. So take it away, Fred.
Daryl. So pivoting from this streaming pipeline that we have here, right? We're going to start from SysFlow all the way to the graphs and then to the contextual rate limiting. Let's dive a little bit into how those contextual structures are created, right? So here you see the graphlets as one important data structure, a stream-based data structure that we create as we ingest new SysFlow records. And those graphlets essentially provide the context for deciding when to forward records downstream to the pipeline, right? And they do so by coalescing process events, file flows, and network flows based on their control paths. So what you see here in this figure, for example, is one exemplar graphlet for the Apache container, which captures the fact that you have a master process, which is cloning many worker process, and those worker processes are interacting with the file system, which is depicted by this file flow node here in the bottom, and also connecting and interacting with network endpoints through this network flow node here in the bottom. So what those graphlets do, then they encode provenance chains, right? They talk about the notion of provenance, parents, children, and they also allow you to further summarize and contextualize the file system activities with respect to that position, let's say, in that provenance chain. So the graphlets are labeled direct, is a labeled direct graph. As I said, they're created in memory and they are created in this stream fashion as we ingest new SysFlow records in the SysFlow processor. And events in the graph, for example, the clone event here, they are labeled edges that associate two processes. So here you can see two process nodes inhabited by their corresponding process instances. So this process node here reflects the notion of a worker process that has, in this case, five inhabitants. And flows, here denoted with those dashed edged lines here, they are basically they connect or associate a process node to the file system and to the network activities. Well, this is important in terms of an organization because they allow us then to make decisions about when to forward and when to not forward, and also how to summarize and reduce this data based on a notion of context, right? So we're going to see how this works in a second. So this is the architecture of the rate modulation strategy that we adopted in the graph engine. So as we are streaming new SysFlow records, we have this graph that is structured that is being fed. And by construction, by design, those graphs basically know where each of those incoming records are associated, which node they will belong to, based on the notion of provenance, control flow, and so on. So there's an algorithm to match them against those nodes. And in each of the nodes, we have those sketch data structures that are used to decide which records to immediately forward downstream and which records we should accumulate for a delayed summarization that we're going to be also forward downstream. So this gives us the opportunity to address two problems when it comes to trying to monitor system events and endpoints. The first one is to cope and deal with heavy hitters. So behaviors that deal with interacting too many times in a short period of time with a specific resource. So you can think about writing or reading too many files from a file in the file system, or basically interacting a lot with a specific endpoint in the IP address space. Another problem that those regulators can help us mitigate is the problem with the scanners, right? So you can think about an antivirus is scanning an entire file system. They will create lots of file flows in a big spatial dispersion. And what these regulators will help us curb down is basically this big number of events that would otherwise be streaming downstream and potentially generate lots of alerts and other things. And finally, at the end of this rate modulation strategy, we have the rate limiter proper, which helps us address via token bucket algorithm with reservation. It helps us address the problem with bursts, right? Sometimes there is a heavy workload, sometimes there is a number of events being collected from the endpoint, and you want to make sure that it's bounded to an upper limit in terms of the rate in which we actually forward that data upwards or downstream. So to talk a little bit about the node level regulation that we perform, we use those sketch data structures, right, that basically allow us to very quickly and effectively decide which records are being forwarded and which ones we're going to be archiving for further summarization or semantic reduction. And sketches are basically data structure designed to store a set in a sublinear size using these probabilistic data structures, right? And in other words, sketches store can store a set in a massive set in a relatively small memory footprint, but typically they provide an approximate answer to queries, existential queries in this set. So they are not reversible, so you cannot ask a sketch if a particular value is stored in the sketch, but you can ask if a value X appears in the sketch, and if so, approximately how many times. So they are ideal to queries like, oh, haven't I seen this before? And so on is very important and effective in filtering the data. So we use two types of sketches in our node regulators. So the first one is the hyperlog sketch based on Bloom filters. And this allows us to basically estimate the cardinality of the set and therefore allows us to help curb spatial dispersion, right? Make decisions about when the data, for example, in a file flow node is covering too much of the file system. And the count mean sketch is then used as well to estimate the frequency of hits on a particular resource. So that allows us also to make decisions about heavy hitters. We use another data structure to perform semantic reduction. And I'm going to talk about the try here, which is a data structure that allows us essentially to organize how the different file system access or file flows are basically stored or dispersed in the file system. So tries are ideal for searching, has been used a lot in routing problems, in network routing. In this case, we use tries to basically organize file system paths and associated with each node of the try, the leaves of the try, values that reflect counts and metadata that would further allow us to reduce the file flow stream that comes out of this engine. So very important in I/O, right? I/O tends to be very, very big in endpoints. So this helps us, for example, extracting regex, aggregating further the file flows that SysFlow is already creating for us by collecting from the system calls. And lastly, as I mentioned before, we're using a token bucket limiter to basically decide and basically smooth out the rate through which these events go out of the regulator. So that's basically a funnel, if you can think like a first in, first out queue, where we can basically decide when to send events forward. So this graph modulation algorithm, if you will, is implemented as a SysFlow plugin. So SysFlow supports plugins. Like Sterl said, the processor already comes with a number of built-in plugins, like the policy engine is one of them. In particular, it supports the automatic tagging of MitraTTP policies. And in the middle here, we created this new plugin that basically customizes this pipeline to implement the modulation. So we have SysFlow records coming in and then SysFlow records coming out, and this is modulated by this rate limiter. So in the evaluation that I'm going to show you on a Kubernetes cluster, you're going to have two deployments of SysFlow, one that has the graph modulation and one without it, right? And we'll see the differences and the impact that this new modulation approach has on the number of events. So just to talk a little bit about this evaluation, this is a Kubernetes cluster that we are monitoring with SysFlow. This is 100 minutes duration or session of monitoring that I'm displaying here. It's a 12 worker nodes cluster. So there's 12 instances of SysFlow deployed in this cluster, so monitoring each of the work nodes, so we have full visibility. It monitors both host and container processes. It has pod metadata and so on. This cluster has lots of infrastructure and user pods. So it's a big cluster with some interesting workloads. In terms of metrics, just to understand this table here, I'm going to be talking about events that we, based on the rate modulation, we decided to forward immediately. Without rate modulation, we forwarded everything, right? Then we talk about accumulation. So things that we decided, okay, we're going to buffer into that node level regulators, and then further semantically reduce, and that's the number of events that are reduced, and then forward downstream. And alerts are basically, once we have either regulator or not regulator, just forward, right, the SysFlow records onto the policy engine. I'm going to be talking about how many TTPs, based on our TTP policies that is open source in the SysFlow process, we are triggering, right, based on those SysFlow records. So if you look here at this table, you'll see that there is 2 instances of SysFlow, right, or 2 scenarios, one without and one with modulation. The number of SysFlow records that were basically collected in this 100-minute period was in the order of 4 million records. So in other words, if we're just collecting SysFlow records without any modulation, we would be streaming SysFlow records at a 687 events per second rate, right? Now, with modulation, what happens is that out of this 4 million plus SysFlow records, using the graphlets, we were able to basically decide that we wanted to forward just 27,000 and some records immediately, because they were unique. They had some notion that they were describing new behaviors that we're observing. And then from those, for 3.5 million SysFlow records, they were basically accumulated and further reduced in 44,000 SysFlow records. So that's a significant reduction. And essentially, the output of that graph engine, right, the modulator engine, is 72,000 SysFlow records, as opposed to 4 million plus records. So the event per second rate that we are now streaming downstream in the pipeline comes from 687 to 12 events per second. So this is interesting. Now we want to see a measure of quality, right? Are we actually capturing all the behaviors that we like to observe, right? I think that's a fair question to ask. And that's where we're trying, for example, to use our own policy engine to measure that. So we have 53 rules, TTP techniques that are mapped into our policy engine. And here you can see that we're streaming basically either this first scenario, 4 million SysFlow records into this policy engine versus 72,000 records into this policy engine. And what you get here in terms of alerts, right, is 100,000 alerts versus 2,000 alerts, or almost 3,000 alerts in the case where you have modulation. So this is an interesting thing. So we are basically cutting out, and I didn't mention that, but there is no, the unique set of alerts is the same. So basically, we are not alerting less or more in terms of the types of alerts. So we are alerting the right things, but we're alerting much less than without the regulation. And this is because there's lots of duplicates, there's lots of redundant behaviors that we are capturing without the regulation. So that's also very important for event fatigue, right? If you're streaming this over themes, then you have much more concise and much more, I guess, compact information that is being sent downstream. Some observations. Our architecture would eventually drop events, of course, if the token bucket exhausts, the rate or surpasses the rate that is set. But in this scenario, which is pretty massive, we had no event drops, right? So just the modulation itself to the graphs and the reduction that we achieved by means of the graph were enough to curb the event rate to a very small event rate. The stream modulation, as I said, drastically curbs the number of duplicate events, and it does reduce the resource usage. So instead of being processing 4 million records over the policy engine, now we're processing only 72,000. So the impact in performance is actually also significant. So just to conclude this talk, this is a preliminary kind of show of what this self-regulation architecture can perform. This was built on top of this open source project called SysFlow. Terry and I were maintainers of the project, so you can find more information about the project online. But there is a growing set of APIs that people who are interested in data science, understand behaviors from endpoints, understanding more about what is going on in their Kubernetes environments, in their host environments, essentially understanding the security posture they can leverage to build. We've shown last year that you have, Python, Jupyter notebooks that you can use to basically explore this data and build analytics on top. And it's very easy to deploy as well. You can deploy essentially in most environments that you would have in your cloud native environments using Helm, OpenShift operators, Dockers, and so on. And if you want to join us in this quest to improve endpoint system telemetry, here it is. SysFlow.io. Please join us on Slack. We are more than willing to help with particular use cases, and we're always looking for collaborators as well. So thank you for your time. It has been a pleasure to talk at Full for the third time in a row, and hope that this has steered some interesting discussions as well.
And Terrell, thank you for your great presentation. A little advice for next year: you guys have done the trilogy. Maybe think of a prequel to go back to. I'm not sure how to do that in the network security world, but you're smart. I'm sure you guys can figure that out.